Welcome to Module 2, Lesson 4, Operations with Scientific Notation. So today what we're going to do is we're going to look at what you've learned about scientific notation and what you've learned about operations or your laws of exponents, and we are going to put them together with scientific notation and adding, subtracting, multiplying, and dividing. Okay, so first you have your example where we are going to end up either adding or subtracting with numbers in scientific notation. There are two methods, and the only reason I'm going to show you the other method is to show you kind of why it works. Otherwise, you have to be able to use the first method. You have to be able to show me that you can add and subtract numbers that are still in scientific notation. So the first thing that you're going to do is you're going to write each number so it has the same power. Okay, we want to find, so right here we want to find the total population. So right here we have 10 to the 8th, here we have 10 to the 7th, and here we have 10 to the 8th. So I would rather change 1 instead of changing 2. So I'm going to change 10 to the 7th to become 10 to the 8th. So 3 and 1/10 times 10 to the 8th is going to stay the same. And 1 and 1/10 times 10 to the 8th is going to stay the same. But 3 and 38/100 times 10 to the 7th is going to change. Now to change it, I want my exponent to go up, which means I have to move my decimal one more place to the left. So if I move it one more place to the left, that becomes 0 and 338 thousandths. So 0 and 338 thousandths times 10 to the 8th. Now, since all of my exponents are equal, Thank you. Excuse me. Now, since all of my exponents are equal, I can add all of my multipliers. And my multipliers in this case, I'm sorry, not this one, being the 0 and 338 thousandths, the 3 and 1/10, and the 1 and 1/10. Okay, so I'm going to line it up over here, 3 and 1/10, 1 and 1/10, and then 0 and 338 thousandths. Okay, so I add the extra zeros here, so I get 8, 3, 5, bring down the decimal, and 4. So my answer would be 4 and 538 thousandths times 10 to the 8th power. So that tells us that the total population is 4 and 538 thousandths times 10 to the 8th power people. Now, the reason why we have to change the exponent is to make sure that all of our place values line up. So if you think about it, when you extend it, so I'm going to go to method 2, when you extend it and you look at these numbers, Canada has one less digit than the other two do. Since it has one less digit, that means that this 3 can't line up with this 1 and this 3. It has to line up with this 1 and this 1. In order to have done that, we had to move that decimal one more place to the left like we did. So notice we moved it one more place to the left. So now those 3 numbers lined up just like they would if we had extended it to standard form. All right, so now what I want you to do is I want you to try this one on your own. You're going to use the population in the table above to see how many more people live in Mexico than in Canada. So what you're going to do is you're going to go ahead and try it, and then when you come back, you can check your answer. All right, so you should have gotten 7 and 62/100 times 10 to the 7th power more people. What you should have found is that you were going to subtract, and you were going to subtract 1 and 1/10 times 10 to the 8th minus 3 and 38/100 times 10 to the 7th. Now, to do that again, we need to make our exponents the same. In this case, I'm going to make my exponent smaller because instead of going up with 7, I want to go down. So typically with subtraction, I would just go and make everything, or I would go lower. So change the 8 to a 7 because then you're not messing with numbers that have no whole number. So here, in order to make this 8 turned to a 7, I have to move my decimal once to the right. Then this became 11 minus 3 and 38/100 times 10 to the 7. So now I can ignore, and I can do 11 minus 3 and 38/100, add my zeros. So I have to borrow from the 1, it becomes an 11. Borrow from the 11, it becomes a 10. This becomes a 10. Borrow, it becomes a 9. Okay, I have 10 minus 8 is 2. 9 minus 3 is 6. 10 minus 3 is 7. And then I keep my same exponent, or my same power of 10, to get my answer. Okay, so again, when you're adding and subtracting with numbers that are in scientific notation, you just have to make it so that way your exponents are the same. But when you do that, you have to make sure to move your decimal. If your exponent is getting bigger, your decimal moves left. If your exponent is getting smaller, your decimal moves right. All right, so now we're going to take a look at this problem, and I know that you have everything written in for you already. What I would like you to do is get a separate sheet of paper at this point so you can follow along with this and write it down on your own. If yours was already made blank, then continue working in your packet. So now we're looking at examples with multiplication and division. We know that the law of exponent tells us that if we're multiplying or dividing numbers with the same base that have an exponent, that we can use addition and subtraction. So if we're dividing and the bases are the same, we'll subtract the exponent. If we're multiplying and the exponents are the same, or the base is the same, then we'll add the exponent. So think about scientific notation. Scientific notation always has 10 as a base. So if you're multiplying or dividing numbers that are in scientific notation, your base is the same. All right, so let's read the problem and we'll actually try this and we'll see what this looks like. So here we have the sun makes an orbit around the center of the Milky Way. It travels 2 and 25/100 times 10 to the 14th kilometers. The orbit takes 225 million years. And I want to know, at what rate does the sun travel? So at what rate does the sun travel? And I have to write my answer in scientific notation. Now I could take my numbers and put them into standard notation, but why? Why mess with all those extra zeros and garble it up so much? Okay, so we did our ride. So first we read and we highlighted. So that one's done. Now we're going to identify that important information. So the important information here, if I want to know at what rate it travels, for rate always equals distance over time. So I need to know the distance. Well, it travels a distance of 2 and 25/100 or thousandths times 10 to the 14th kilometers. And then the time in this case is 225 million years. So years, kilometers. All right. So now, in order to figure out its rate, I told you that we know that it's distance over time. So I know that I have to divide. So we did our I. So now we're going to determine a plan. I'm going to take my distance, which was the 2 and 25 thousandths times 10 to the 14th, and I'm going to divide it by, and I'm writing it in fractional form so that way it lines up nicer. And I can show you what I'm talking about when it comes to the scientific notation division. So in this case, it's 225 million. Well, let's write 225 million as a number and not in words. So 225 million means I have to have 6 zeros after it. In order to write this in scientific notation, my decimal has to go between the 2's, and that means that the exponent is 1, 2, 3, 4, 5, 6, 7, 8. So my decimal in this case is going to, or my exponent is going to be 8, so this is 10 to the 8th power. And then this is 2 and 25/100. So then now what I can do, since my bases are the same and I'm dividing, I can do 14 minus 8, and I know that gives me 6. So I get 10 to the 6th power. And then all I have to do is divide So 2 and 25 thousandths divided by 2 and 25 hundredths times 10 to the 6th power. Okay? And when I do that division, and I'm not going to do the long division right now, I'm going to do the division in the calculator. When I do that division, I get 0 and 9 tenths times 10 to the 6th power. Now I have to write it in scientific notation. Even though we think it's in scientific notation, this number is not between 1 and 10. It's less than 1. So I have to move my decimal once to the right, which means my exponent has to change and it has to go down 1. So my answer in this case is going to be that the sun travels at a rate of 9 times 10 to the 5th power kilometers per, and it's years. Whoops, so kilometers per year. So again, as long as your bases are the same, which they always will be with scientific notation, you can subtract your exponents and then just divide your multipliers. All right, so I want you to go ahead and read, make sure that you do your ride and determine your important information. Eliminate any fluff information, identify those numbers that you're going to have to use, show your work, and when you come back, we'll check your answer. All right, so you should have come up with 8 and 928 thousandths times 10 to the 8th power miles, and 3 and 14 hundredths times 10 to the 2nd power minutes. In this case, if light travels at a speed of 186 times 10 to the 5th miles per second, it takes light to about this long to reach Saturn. Find the approximate distance from the sun to Saturn. So what you're going to do is you would multiply. You would say, okay, well, this is how far it has to go, times 10 to the 5th, times it has to go, and it goes at a rate of 1 and 86 hundredths times 10 to the 5th miles per second. Line up your like terms. So in this case, these are the same. So I have 4 and 8 tenths times 1 and 86 hundredths times 10 to the 5th times 10, and this should be to the 3rd. To the 3rd. Okay, so when I do 4 and 8 tenths times 1 to the 6th, that's when I got the 8 and 928 thousandths. And then, because of the fact that I'm multiplying, that tells me that I can add my exponents, which means I get 10 to the 8th. In this case, the light travels at this speed, okay, and in order to find how long it takes, so distance equals rate over time. So since that's the case, if I know the rate and I know the distance to figure out time, what I would have to do is I can say, okay, well, I'm going to take both sides and multiply them by time. That gives me t times d equals r. And then if I divide both sides by distance, that tells me that to find the time, I have to take rate and divide it by distance. So I'm going to divide. I'm going to take my rate, 1 and 1/17 time, or 1 and 17 hundredths, times 10 to the 7th divided by, and this we have to turn it into backwards. We have to turn it into scientific notation. So 1, 2, 3, 4, 5, 6, 7, 8, 9. So we have 3 and 67 hundredths times 10 to the 9th. And we're dividing that by 1. And this is backwards. I apologize. This should have been distance divided by rate. And then we divide that by 1 and 17 hundredths times 10 to the 7th. And again, we divide these and subtract these to get our answer. So now we're going to take a look at how do you write this on a calculator in scientific notation. So this is going to be a really quick part. With scientific notation on your calculator, typically you are going to see the label EE as lowercase letters or uppercase letters. When you see them on your calculator like that, so if you have a number like this, you can change it, or you can use it in your calculator when you type it in. You can type that in as scientific notation. So let's take a look at our calculator here. And I actually don't have a scientific calculator on my board. So what you have to know is that you have to type it in. So I would find on my calculator, I would type in 4 and 4/10, and then I would find this button, this EE button. And I would hit it, and on the screen, it's going to show a big E. And then I type in my number. So in this case, my exponent is 13, so I type in 13. Okay? So let's go to the U-try problems real quick. This is actually pretty simple when you start to get the hang of it and when you have a calculator in front of you. So in this case, to type it in a calculator, into calculator notation, this would be 7 and 5/10, capital E, 5. Then to take this one out of scientific notation, I would do calculator notation, 4.5 times 10, and then my exponent is -1, so times 10 to the -1. So I want you to go ahead and try the last 4, and when you come back, we'll check your answers. All right, so here are your answers. All right, there's really nothing much to go over. This is what you would type into your calculator in order to make this happen. And if you see this on a piece of paper, then you know that this is what it means when you're handwriting it. All right? What I would like you to do is I would like you to do all of the guided practice problems. Right? Make sure that you write them down and finish them in your notes first, and then transfer your answers to the Google document or the Google form, and make sure that you turn it in before class tomorrow. And as always, if you have any questions, please be sure to write them down or to email me so we can go over them in class.